During the previous video, you've learned about sensor technologies. In this video, you will learn how to apply those formulas in actual sensor problems. First off, we have capacitive sensors. For the capacitive sensors, we have three parameters. We have the area of the plates, the distance between the plates, and the material dielectric between the plates. The material dielectric is an intrinsic quantity that depends upon the material that is used to separate the plates. So for the capacitive sensor formula, we have capacitance is equivalent to the dielectric material multiplied by the area and divided by the distance. Let's take a look at this problem. What is the capacitance of an empty parallel plate capacitor with metal plates that each have an area of 1 meter square and separated by a distance of 1 millimeter? So for this, we have to apply our formula that capacitance is equal to the material dielectric times the area divided by the distance. But what are we going to use as the material dielectric? It is stated in the problem that the space between the parallel plate capacitors is empty. So we're going to have to use epsilon naught, or the dielectric constant. We have epsilon naught equal to 8.85 times 10 raised to the negative 12, and the unit is farad per meter. This is available in most calculators, and it has the symbol epsilon naught. So once we have this, we also have the area, 1.00 meters square, and the distance, 0.001 meters. We can plug everything in our formula. So we have capacitance is equal to 8.85 times 10 raised to negative 12 times 1 divided by 0.001. Notice that the units must agree with each other. So if one is in meters, we have to convert everything else in meters. So in this example, the distances are converted to meters and the farad stays as is. So if we calculate this, we get capacitance is equivalent to 8.85 nanofarad. And this will be our answer. So we have resistive sensors. For resistive sensors, we have the formula R, this is our final temperature, is equal to R sub 0, this is our initial temperature, times the quantity of 1 plus alpha. Alpha here is the temperature coefficient, times the quantity of the final temperature, T, minus the initial temperature, T sub O. Now let's take a look at this problem. A platinum resistance thermometer uses the change in resistance to measure the temperature. Suppose R sub 0 is 50 ohms at T sub 0 equals to 20 degrees Celsius. Alpha, or our temperature coefficient for platinum, in this temperature range is 3.92 times 10 raised to negative 3 degrees Celsius raised to negative 1, or per degree Celsius. The question is, what is the resistance when temperature is equal to 50 degrees Celsius? So now we have to recall our formula. R is equal to R sub 0 times the quantity of 1 plus alpha times the quantity of T minus T sub O. So we have all the variables in our given. We have to directly substitute the variables. So now we rewrite the formula and we substitute all the variables. We have 50 times the quantity of 1 plus 3.92 times 10 raised to negative 3 times the quantity of 50 minus 20. This is the final temperature minus the initial temperature. So now we plug this into our calculator and we get R is equal to 55.9 ohms. Now take note, the unit for resistance is ohms. And that's it for resistive sensor problems. Now this is the end of sensor calculations.